So k here equals 1, 2, 0, 1, 2, 3 here denotes that your rewiring, your basically your friendship, the friendship that you maintains with people who are not in his neighborhood, the friendship that you maintains is sort of it is based on the distance of that node from you. Further away the node, less probable is you being friends with them. For example, let's say this is a node which is some 10 units, 10 distance away from you, and this one is some 20 distance away from you. So this is less probable and this is more probable. Okay, that's what this distance function captures. Okay, and for a fixed k, so what do we mean by this? If the distance is, let's say 5 here, let me write that down. So if this distance is let's say 5 units and this one is 10 units, the probability of you being friends with V is more than the probability of you being friends with this person. Okay, let me give him some name. Let me call him W. This person is called, let's say this node is called W. Okay, the probability of you being friends with V is a lot more because it is closer, just 5 units away. By 5 units I mean 5 edges away. It is not just one edge. Okay, in case you and V are 5 edges away, then you put an edge between you and V based on a probability function. Okay, what is a probability function here? Nothing, it's very, very simple. You judge whether you want to put an edge or not by looking at the distance from you. This is far away from you. This is 10 units far away from you. This is 5 units closer to you. This is more probable to become a neighbor of you. V is more probable to become neighbor of you than W. What decides this? It is this equation that decides this. So 1 over, if let's say assume k equals 2, then 1 over 5 square is the probability of you being adjacent to V. And 1 over 10 square is the probability of you being adjacent to W. That is if k equals 2. If k equals 1, then 1 over 5 is the probability of V being adjacent to you, and 1 over 10 is the probability of W being adjacent to you. Okay, let us not worry much about this fact. Let us only observe the following. All I am saying here is there is a node here, and he is of course friends with his immediate neighbors, a few of his immediate neighbors. All right, very clear till here. And all that I was saying before is that he also takes part in being friends with faraway people. Let's say a few of them. Few friends are faraway people for him. But then that friendship simply depends on the distance. Okay. By that I mean, further away they are, less probable that this person is friends with him. Who decides it? I am going to decide it based on the inverse of the distance. So if let's say in plain English language, if this is some 5 kilometers away, this is 20 kilometers away, the probability of friendship here is rare, probability of friendship here is more probable. Okay, so once I give you a nice example, you will realize what is happening here, what is the motivation for this distance function. Okay, all right. So here goes the right motivation. Assume there is a city. You are a city planner. Let's assume you are a city planner. And this is the city. And here is the center of the city. Alright. And you may want to go to different places here. These are all different locations. For the time being, just forget the graph here. We are not talking about a graph. We are just talking about, let's say, we are planning a newly built city. The city is newly built. I am planning some road networks here. Public transport here to be precise. Let's plan some public transport here. So now, assume this is your house And this is some market, a supermarket or a shopping complex or whatever you want. Now you want to go from here, from your house, you would like to go to market. Of course, you can take your car and then go, but the point is you would like to use public transport. There are so many locations here. As you can see, there are, let's say, hundreds of locations here. You cannot basically put a bus, a public transport bus, from any node to any other node here. From your home to market, you may not have a bus. So, let's say you may want to go from your home to, let's say, some other place and to some other place and then reach the market. So, buses don't ply between any two locations. Now, here is the question. If you were to decide what should be the bus routes, if you were to decide the bus routes, what will be the locations from which you will deploy a bus, right? Assume every single location has the same amount of people and the requirement for them to travel is also the same. What exactly will you do? How will you plan the bus routes, right? Assume you have some 100 such locations here. There are 100 such red points, whatever you are seeing here, 100 such locations. So, whatever points you are seeing here, assume there are 100 such points and you cannot simply put buses from any point to every other point, right? That's not feasible. That's not practical. So, what you do is this. Assume this is the city. All you do is there is a central bus stand. Let's say this is the central bus stand. Alright, and then from here you will have a bus go to this place, this place, this place, this place, this place, and this place. That's it. Right? These are the several locations where your buses go. Alright, and then do you see something here? Do you see that there are concentric circles here, and you're trying to ensure that you have a bus for every possible concentric circle, correct? So what do I mean by this? By this I mean, if you let's now take a grid which is easy on the mind. Assume there are some locations here. You would ensure that there is a bus that goes to concentric circles. So what do I mean by that? By that I mean from this center, let's say from the center, there are buses which go just to the next location, next to next location, next to next location, next to next location, so on and so forth. Okay, you will try to cover all possible locations from here, correct? All possible locations. I'm not drawing it well, but you basically are getting the right intuition, right? So that you're basically covering all possible areas in the place, and the bus will go there, and from there you may want to take another bus. Simply, very simply stated, assume there is a metro service where you need to go to, let's say, this place. Okay, metro starts from, this is the start and this is the end. Let's say it's linear, it's just it's straight like this, and you need to go here. You need to go here, but a metro train goes to this location, and let's say it goes to this location. Okay, these two locations, let's assume. But then you may want to get down here and then take another metro to another station, but that station goes a little further away. And from here you can always come back to another station, and that station probably takes you to further away place. There probably isn't any metro from here to here. So as you can see, you need to reach this place starting from this place. But the metros are very weirdly distributed. Some super fast metros, they don't stop. They don't stop. From here, they directly take you here. And then from here, you can only come here. And from here, maybe there is a train to this place and another train to this place. See, it's very complicated. How would you come then? So then you would probably take a metro to this place and then travel to this place and then travel to this place. You may have to take a detour here. You see, this is how things work. That's because if your reach is high, by that I mean, see, if you have longer routes, people may want to come back from it. Okay. If you only have shorter routes, let's see what happens. If there's a shorter route from S to E, exactly the same thing. Okay, let me just replicate this and then put it here so that it's easy for us to work. I will copy paste this and let me give you another scenario where every single route is fairly short. Okay, it's fairly short. So what do we do in that case? That comes with another baggage of problems. Right? Let me once again copy paste this, copying this and then pasting it, and then I'm going to tell you that what if these were not the paths? Let me remove these paths, and I need to go reach the same destination, right? I need to come and reach here. All right, I want to start here, but then the metros are all like this. And there's a metro to this place, and then another metro to this place, and then from here there's another metro to this place. Okay, so on and so forth, from here to here, and then again from here to here. All right, you may have to do a whole lot of toggling. You see, a hell lot of toggling you may have to do from here and then to here, and then there is a metro to this place. All right, so you may have to do a lot of jumps here. This is a very strenuous process, right? This is a very, very strenuous process, as you can see. Why is that? There is no quick way of coming from here to here, right? If there are some 100 locations here, you cannot put 100 choose 2, 100 C2. Let me write that down. You cannot put 100 C2 number of trains or buses on this road. You can only put a few buses or trains between stations. Correct? The above one has a problem that if you put super fast trains, you may have to go ahead and then come back. While here, you may have to do a lot of hops. It's a lot of waste of time. You see, you need to get into a bus and then another bus and then another bus and so on. You need to do a lot of hops. What is the ideal way to construct metro service here, right? So what we will do is, if you observe this problem this is one dimensional, you see, starting from here and going to here. If you see the same problem in 2 dimension, let's say assume you write a square or a circle to represent a city, right? We have exactly the same problem, that when you want to put buses from one locality to the other, right, it's a huge issue. From where to where will you put? Okay, from where to where will you put? So let's do one thing. Assume you were to write a program to accomplish this. So what will you do? You will first generate a small world network. Let's say a small world network with some rewiring probability. Okay, P is the rewiring probability, you will indeed get some graph here, right? You will get some graph here, all right? So let us write that down. I get some graph here, right? I get some graph here. Let's say a huge graph here, correct? And then I can go from any node to any node, right? To any node. But I must ensure that I can go from any node here to any other node here. From any source to any target, I should be able to go. Okay, from the source target, I should be able to go. And I want my edges to facilitate this. That's the whole point, the edges to facilitate this. So how does a small world network look like? It will have a lot of edges to its immediate neighbors geographically. Okay, look at this. This is a city, and closer the vertices, more are the possibility of edges. But then here and there, I do put edges to further away nodes too. Okay. Now what I will do is, let me assume that I put 10, I take 100 cross 100 grid, right? 100 cross 100 grid, whatever this was, if you remember, okay, a huge grid. I'll take a 100 cross 100 grid. Then what I do is I basically will do this. Let me write that down. It's slightly involved. You will understand it better if you get the next 2 minutes of my explanation. So this is a 100 cross 100 grid, let's say, right? And every single node here, let's say every single node here is adjacent to some, let me say, 10 nodes, 10 nearest nodes, whatever they are on the grid. All right, 10 nearest neighbors. What do I mean by that? So all these people, and maybe at 2 levels. Okay, let us say some 1, 2, 3, 4, 5, 6, 7, 8. Let's say some 20 neighbors, 20 nearest neighbors. Okay, this is the homophily part. 20 neighbors. Okay, and then it also is adjacent to a few nodes further away, and this is decided based on the probability function 1 over d to the k, where k can be 0, 1, 2, etc. as I told you, right? What should be the ideal value of k? If I were to run this particular experiment on a 100 cross 100 grid, right, and I'll choose first k equals 0, what will happen? When k is 0, this entire thing will be 1, which means it will be the same probability with which you will be picking vertices further away. It's uniform distribution. That can be dangerous, you see. Why? You will randomly put roads between 2 nodes. Then you may have to go longer distances and then come back if you want to come to the destinations. Alright? It may not really serve your purpose. If you put k equals 1, then a node that is 10 units away and a node that is 20 units away. 10 units is more probable because it will become 1 over 10 probability. 20 units will be a lot improbable because it will be 1 by 20. Okay. Now instead I take k equals 2. Then it becomes let's say, assume this was 10 units and 15 units or 20 units, whatever, anything you want. Then if you pick k is equal to 2, this becomes the probability of this being friends will be 1 over 10 square. The probability of this being friends will be 1 over 15 square. But then again there's a problem. There won't be very further away nodes because 1 over 15 square is 1 over 2 to 225. And that's a very small number, which means a node that is 15 units away. By units, as you all know, I mean the number of edges. the shortest path length. If a node is 15 distance away, then the probability of that being friends is 1 over 15 square. But a node that is 10 units away is 1 over 10 square, which is 1 over 100. This is more probable. This is way less probable than what it used to be when k equals 1. As you can see, if k is equal to 3 or more, nodes that are far away becomes very, very improbable. Okay, and navigation becomes difficult for you to go from a source to a target. So here goes our question. We were talking about simulation, right? Continuing our discussion, if you were to go from a given source to a target T, target node T, and you have considered different case, k equals 0, k equals 1, k equals 2, 3, 4, and assume you draw this plot. Okay, assume you draw this plot of this y-axis versus the x-axis, right? And then you will plot what are the path lengths if you put on x-axis you put k, which is basically 0, 1, 2, 3, 4, etc. Okay, 1, 2, 3, 4, 5, and so on. And on y-axis you put the, let's say, the distance. The distance covered when you take the typical search algorithm, when you go to the next node and then you check how far is the target, and you go to the next node that is closest to the target, and so on. When you do this, you will observe that when k equals 0, k equals 1, k equals 2, etc., the plot looks like this. Okay, let me write it nicely. The plot actually has the observation is at 2 it says something, the distance is minimum. Now what do I mean by distance? By distance I mean you need to, your destination you can go and reach quickly if the rewiring probability is 1 over d to the k, where k is 2. Okay, when k is let's say 3, the distance is slightly more, as you can see. When k is, let's say, 4, then the distance is a lot more, as you can see. Okay, I hope you are understanding what I mean by this distance. By this distance, I mean the path length of the process. When you want to go from the source to the target, it is a longer path if you were to choose k as 4. If you were to choose k as 2, the path from S to T. What do I mean by path from S to T? The same old Milgram experiment. When you take a node and you go to the next node which is closest to T on the grid. Okay, of all the neighbors, you choose that node that is closest to T on the grid. That is what we have been discussing all this while. Right, and this particular algorithm will tell you, this particular programming exercise will tell you that a k equals 2 is the best possible value for k whenever the rewiring probability that you are considering is given as 1 over d to the k. Right, so this is sort of a hand waving that I have done here. In fact, there is a very beautiful proof for this, saying that k equals 2 for grid and k equals 1 for one dimension. And the textbook describes it. It is very nicely described with some very basic probability. You can understand it completely. Let me know if you haven't understood it. I will help you out understanding it. But this will be out of your own interest. This will not be part of the course examination. But the idea here is simple. The idea here is that you use k to sort of decide on whether you will make friends with nodes that are further away. Alright, and when you make friends with nodes that are further away a lot more, then you are in trouble. A lot less, you are in trouble. The perfect balance is when you choose k equals 2. Okay, in fact, we will be showing you a programming exercise where we will be explaining this in detail. It will become probably clear to you then. As of now, just know that this curve is how it looks like, and for 2, the distance is the shortest.